All right, let's get started. So just a couple announcements. So there's a homework due tonight. So that homework will actually go over some of the bonus stuff today, if that's helpful. But then these slides have been online, and there's some videos that are sort of available with that. So you can feel free to check those out as well. And then if you choose to do it, there's an interactive Canvas activity that will be due before lecture C1. So this is B3, so C1 is next lecture. So again, there's a bunch of those you can drop. So if you're not interested, that's fine too. But if so, it gives kind of practice on stuff we've done so far, and then helps you kind of go over what's coming up in Unit C. Otherwise, I mentioned there are these competitions. So there's the Rockwell Arena competition, which is a great alternative for the final project. In other words, you can use this as your final project submission instead of coming up with your own system to look for. And there's actually some monetary rewards. If you're interested more in healthcare and you're willing to learn a different simulation platform than the one that we talk about in this class, FlexSim has got their own that's focused on healthcare, and so that is another option. And then Simio has their own competition down here. So all of these, if you let me know ahead of time that you're planning on forming a team, then we can make sure that we've got, that there's enough spots, especially in this arena one, where you can only have 3-person teams. We have to make sure that it works with your lab section. Then we can consider these for your final project. With the caveat that we only will be talking about Arena formally in this class, and so FlexSim and Simio you have to learn on your own, but the fundamentals are the same in both of these platforms. And some of the TAs may actually have experience with these as well. Any questions about any of the assignment stuff? Yeah. Absolutely, yeah, great question. If you're looking for team members, your team members have to come from your lab section, but you can feel free to, if you don't want to ask around your lab, or you don't think people are necessarily coming to your lab, or everybody you could go pick from, feel free to use the discussion boards to look for team members as well. We won't actually ask you to form your teams till after the midterm. The midterm is like October 8th, so there's still time. But the first thing we ask you to do is to sit an assignment where you sort of you fill in your teammates, and so I'm sure there'll be a lot of activity then. But if you want to think about that, then yeah, feel free to post to discussion boards, make use of Canvas, however works for you. Yeah.
How many people are on a team?
Nominally, so the goal is 4 people per team, and so if you've got 4 people, then you don't need any approval from me, and then that allows us to be sure we have enough time in the lab section to present. If you want a 3-person team, we can allow a certain number of 3-person teams per lab, just depending on how many people are in that lab. So you have to check with us ahead of time, and it's kind of a first come, first serve sort of thing. So at some point in time, I'll run a little LP to figure out what's the max number of 3-person teams we can have per lab section. And then if you come to us and say, I really want a 3-person team, then we can slot you out for that. There may still be a case that the way things work out, there happen to be 2 people left over, and then we may have to reassort them. So just because you had a 3-person team, that might mean you have to fold someone else in later, but most people who ask for 3-person teams early get their 3-person teams. Other questions? Yeah?
Could there be any exceptions to having an additional person that's from a different lab group?
There have been in the past, but I always am hesitant because I can't really ask somebody from another lab group to show up to present in a section since it's not on their schedule. But there have been very special cases where we've allowed that to happen in the past. So we can discuss that offline. Any other questions? Okay, so last time hopefully you should be familiar with these types of outputs. This is kind of what's due on your homework. So we went through a hand simulation example like this. Hopefully it feels very similar to the much more tedious hand simulation that you did on your lab 2. And so by now I hope you can see why we want computers doing this for us and not us. But I hope you also can see that in order really to capitalize on the stochasticity in these sort of inputs that are coming in, we need a lot of lines of this to sort of get to significant variation that starts looking realistic. And so when we were building this table, we were implicitly also filling out a timeline. where effectively what we start with is these inter-arrival times and these service times, and then using the magic of computer simulation, that ends up turning that into this timeline. And some parts of this timeline are relatively easy to figure out ahead of time, like the arrivals. If you think about it, the inter-arrival times, you can line them up end to end, and you'll get all of the arrivals. And so that's also, I guess, another way to check your homework, is that you kind of know when all the arrivals will be without even simulating the thing, because it's just the kind of cumulative sum of the inter-arrival times. The first one's at 0, the second one's at 4, then you get 6, 7, and then 7 plus that 9 gives you up to 16. So that's how our arrivals are set up. Now we call them activities because these inter-arrival times were sort of known before even doing the simulation. So they're activities because we can get a distribution, it might be a statistical distribution of inter-arrival times ahead of time, and that's what makes them activities or inputs to our model. Now there's also these services. Now services are a little more complicated because we don't know when they're going to start. But our services are also activities. So when customer 1 begins service, we know they'll be in service for 1 because that's in the table. When customer 2 begins service, we know she'll be in service for 8 because that's in the table. Customer 2, and so on and so forth. Because we can look at the table ahead of time and figure out what these durations are going to be, we call them activities. And again, we view them as inputs to our simulation model. But if those are the inputs to our simulation model, then what are the outputs? Well, they're these gaps. They're these delays. They're these things that we couldn't really guess ahead of time without going through the simulation process. And so we can see here that just by looking at this table, it's not obvious, well maybe at least it isn't obvious to me, that when customer, so we see customer 1 arrives and departs here, but then there's a gap in our system until customer 2 arrives. So we can still view this as a delay because that's idle time that we didn't anticipate for. So for that whole period of time, our server is just sitting there idle, not doing anything useful. So that is an output. How often does that happen? Other delays that occur, like customer 3 arrives, but customer 2 is still in service. So customer 3 has to wait until customer 2 is done before customer 3 can start again. That we view as an output. That is something we didn't anticipate. Yeah, question?
So I would say that delays are the times that customers spend in the queue.
Delays, I would say, yeah, that would be an example of a delay. So a delay could also be like back here, the time a server spins idle. But those things, the time a customer spins in a queue is another delay.
So that's why we never put waiting as an activity?
Yeah, that's right. That's why anything that sort of sounds like, I'll use the term later today as a conditional weight. Anything that is a weight that depends upon the state of the system. So the only reason you're waiting is because the system's busy. If it depends upon the state of the system, then it's a delay, not an activity. And the only reason we use these terms is to help you distinguish between input and output. And using the terms input and output, they're not quite specific enough because, it's an input and entity and those sorts of things. And so we have these special terms, activities and delays. But really what we mean is what is an input duration versus an output duration. An activity is an input duration, a delay is an output duration. So we have all these delays, we accumulate all of those. Delays of durations that can only be determined after running the sim. All right, so an activity is an unconditional weight. Its duration does not depend upon the system. You can kind of guess it ahead of time. If you were to just ask me, what's the third service time going to be? You could tell me that without even running the sim. But, so we also call this a completion of activity as, well, there are a bunch of different types of events. One of the types of events is a completion of an activity. We refer to that as a primary event. So whenever you start an activity, you must schedule the end of that activity, which means you must schedule an event. So when you're doing your hand simulations, if you're saying, well, at this particular point in time, I am starting the activity of service, you have to make sure that soon you schedule the end of that service. So that means that you're going to add something to the FEL. So if you start an activity, that means you're going to add something to the FEL right when you start that activity, or else the activity is never going to end. A delay, on the other hand, is a conditional wait. And so we don't know when the delay is going to end. We have to wait for the simulation to tell us that it's ready for that delay to end and whatever else to start. So its duration depends upon the system. It's caused by interactions between different activities. So it might be caused by, my inter-arrival times don't quite line up with my service times, and so the arrival has to wait for the next service to finish before the next service can begin. And due to that misalignment, we get that delay. So our job as operations engineers is to try to restructure systems to better align activities so that we get a reduced number of these delays. We can't get rid of them totally, but it's kind of like you can say ahead of time, well, if I went from one server to 2 servers, I could pretty much guarantee that I could handle all my incoming traffic without anyone waiting. That's an example. Or you could say, if I reordered this so that if people were forced to do this before they run through the X-ray machine, so if I just forced them all to take off their shoes before having to remind them later to take off their shoes, maybe that, by forcing them to take off their shoes early, is going to reduce or it's going to change the structure of activities that have to happen later. So it's our job to kind of reorder things in order to reduce the number of delays. And that's what SIM allows us to do, is we can play with these different reorderings without having to actually do them in a real system. So delays do not generate events, but an event can terminate a delay. So if an event has been scheduled to end an activity, it may also end some delay associated with that activity. If that activity is holding up a server, the event that ends the activity is going to also make the server available, which will then end that delay. So we manage delays in hand simulation with these internal lists and state variables, like the checkout line, like NQ, NS, or LQ and LS. And so these are things that allow us as we're running through the simulation, we don't have to look way up in the table. We can look at the current line or maybe the line right before it to see what the state of the system are. And then based on the state of the system, decide, are we going to schedule an activity, or are we going to have to wait on scheduling activity until that activity is done later? So delay emerges from implementing concurrency with limited shared resources. If you get rid of the shared resources, you're probably going to get rid of the delays, because all your activities can kind of take place whenever they start. So, in an airplane, we have to wait to get on a plane because there is just a single entrance. And then once you're in the aisle, there's a single aisleway that we all have to share in order to get to our seats. So it's these shared limited resources that make us wait. And that's what generates a delay. A crosswalk is a shared resource that only one type of entity can use at a time. Only cars can use it, only people can use it. You can't use it simultaneously, at least not safely. And so those two have to wait on each other. And then you can come up with lots of other examples as well. So delays emerge from shared limited resources. Any questions about these distinctions? Activities, delays, the role of resources in delaying entities, etc. Inputs and outputs. And there's also, again, if any question comes up and you don't want to bring it up, you can use this URL or this QR code, and it'll get queued up, and I can either take a look at it in class, if I've got the tablet out, or I can take a look at it afterwards and post on the discussion boards. All right, so generically, for any discrete event system simulation, you basically are going to have a future event list. In tools like Arena, you can actually get access to their future event list for debugging purposes, to try to understand why your system is going to work, why it's working a particular way, but you don't usually directly interact with the future event list unless you're doing a hand simulation. And after Lab 2 in this homework, you're not going to have to do a hand simulation. Maybe on the midterm, I might ask you about hand simulation. I might ask you to fill in a line or to fill in a cell in a hand simulation. But in general, in your career, you're not going to be asked to do a hand simulation, because that's what we have computers for. But once it's in the computer, you do have access to this FEL. What the computer is going to do and what you do by hand is you set the clock to jump ahead, and then you schedule new events based on the future end of any new activities that have been generated at that new event. So if there's been an arrival and if the oven is empty, you can now schedule the oven baking to begin. Scheduling the oven baking to begin, that's scheduling a new activity, so you have to schedule when the baking ends. And so you schedule the end of that. And that just means adding one event to the event calendar. The start of any new service is an activity and must generate a new event to schedule the end of that service. So that's what we're doing. Eventually, when you hit the end, your simulation stops. You can make this end depend on the state of the system, where you can say, I'm going to end whenever this particular condition is met, maybe whenever the Q goes to 0, or you can base it on time, which is the way your hand simulations have gone, just based on time. We did this long example that I won't really go through in detail here, but this is basically the set of events that you would, or the process you go through for any single channel queue. So in a single channel queue, you've got an FEL that's going to have either arrival, departure, or end events. On an arrival, you basically see if the server's available. If it is, you schedule a new departure. If it isn't, you add someone to the queue, and you always add the customer to your checkout line, which keeps sort of a track of who's waiting or in service at the time. If it's a departure event, you keep track of your stats on departures. If there's someone waiting in the checkout line, you schedule a new departure event, and then you move on from there. And then if it's an end event, you terminate the sim and do any other stats. And then that's what you'll go through in your homework to build up a table that looks just like this one. And again, you don't have to generate this timeline in your homework. All we're looking for is this table. And again, just following the book's convention, it's fine to end your table on your homework on the event before the end event. So basically, if you fill out the last line that has an end event as the first event in the future event list, and you can stop there. Questions before we move on to a review of all the terms so far in one slide, and then the new stuff. Okay, so far these are the terms that I'm hoping that you've got kind of in the back of your mind and are pretty comfortable with. System, and so these are also in the back. If you go to the Banks book at the end of chapter 3, they have a review of these topics. And so, just following Banks and just sort of making sure that we're all up to date on system. And we have dynamic systems. So a system's just a collection of entities and resources that interact over time. These are dynamic systems because they move over time. We're building models, which are abstract representations of systems. These are not meant to be perfect representations. They're meant to just capture as much as we can to build sort of a useful model without being so detailed that they're impossible to simulate and impossible to make any conclusions from. So they are necessarily reduced in order for us to gain intellectual tractability as well as computational tractability. We've defined system state, which sort of captures these systems at any instant of time as they change over time. We've said that an event is an instantaneous change in that state, and the clock is one of these state variables that we follow along as we're jumping irregularly throughout time through state changes. We've got entities and attributes. We've got these lists, which are sort of used inside the simulation in these tricky ways in order for us to just manage the bookkeeping. So this is not something we talk about at the abstract level, but at the level of implementation, we often need to think about, well, I need to generate a list right now, a list of customers. And hopefully through the lab experience and the homework experience, you've seen how useful those lists can be in keeping track of who's waiting currently. We've got event notices, which go onto the future event list. That's how the time moves along in this event scheduling worldview. And then we've got this more abstract distinction between an activity and a delay, which again is just the difference between input and output in dynamic simulations where you've got time moving along. So activity is kind of what we know in the input about how long things are going to take once you get to them, and delays are what we know in the output. What's the extra time that the organization of the system has added that's going to prevent things from sort of acting instantaneously? So delays are the result of limited resources. So any questions about these terms? Anybody feel confident they could tell a story in terms of these terms? Moving towards your final project, I'm hoping that you'll start, if you're waiting in line at the coffee shop or something like that, you start looking at the world in these terms. You start saying, that, I noticed that it takes roughly 30 seconds for that particular cashier to take an order. Well, that's an activity. I know that stat ahead of time. I could start doing some operations research on that. I notice I've been waiting for a long time today, and I don't understand why I've been waiting longer today. And then you look ahead and you see, oh, it's because there's one less barista working. Well, so it's an extra resource limitation. So, as you go towards your final project, you're going to have to build a model of one of these real systems. And so, as soon as you can, start trying to think of the world around you in terms like these, and we'll make it easier to build those models. All right. Okay, so we've so far been talking about hand simulation. Now we're going to move into the part of the class where we're going to start actually using computational tools to assist in these simulations. Before you can learn arena and things like that, then we're going to start with something a little simpler. And so you're going to have this spreadsheet activities we'll talk about today. Lab 3, you're going to do Monte Carlo simulations using a spreadsheet. So we start with sort of these spreadsheets. Then in Lab 4, you'll use an agent-based modeling tool. And we'll talk a little bit about agent-based modeling at the end of Unit C. And then we'll get into the heavier stuff where we finally get into arena for the rest of the course. So what is a spreadsheet and how could it possibly be used for discrete event system simulation? Well, when we think about programming languages, there's 3 basic groups. There's the procedural groups, which are like C, Fortran, Pascal, BASIC, which are what we call imperative. And so imperative programming languages, and this is not something I would test you on, but I'm just trying to give you some background here, is that imperative programming languages are ones where you write arguments that formally change the state, and we now know what state is, of the program. And so you write x equals x plus 5. You said that the previous value of x was whatever x was, and the next value of x will be plus 5 from that. And contrast that with object-oriented, C++ and Java, where you've got data structures that carry all of those procedures within them. And so it's less about changing the state of the system and more about sending messages back and forth, where you say, I'm going to turn the lights on. I am going to cause a person to enter the building, that sort of thing, is that we don't actually know what's changing in terms of the state of the program and the variables and all that, but we just instantiate objects and ask those objects to do things. But it still has a flavor of this kind of imperative where we still are thinking about the way the states are changing behind the scenes. The third type, which is a little more abstract, is what we call a functional. And so things like Lisp, Haskell, ML, programming languages you don't often hear about unless you get into sort of more advanced kind of computer science courses. These are what we call declarative, where you don't actually pay any attention to the state of the program. We have no idea how things are happening. We just write relationships between things. Like we just happen to write that a particular list is always the combination of 2 other lists. And we write that those 2 other lists always sum up to 6. And you write all these relationships that you know to be true, and you count on the language to somehow make something happen, but you don't actually know the steps in which it's doing those things. And that is actually where spreadsheets fall. So it's kind of interesting, this functional programming language is a lot of things that people don't even see unless they're like really in the weeds of computer science. But one of the most kind of successful programming frameworks for consumer computing is one of these, and the spreadsheet. So in a spreadsheet, if you think about it, every cell, you just write a relationship to the cells around it, but you have no idea how it's doing the calculations. You don't know which cell it's calculating first, like does it calculate this cell and then this cell, and you don't care. You just write relationships where I say this column is always the sum of these two columns, and so on and so forth, and you just count on the spreadsheet to make it work. So when this came out, it was called cell-oriented data flow programming. The big aspect of this is there is no state because you don't specify steps. Now, of course, you can add in Visual Basic or other sort of scripting, so you do add that, but just a plain vanilla spreadsheet doesn't have any state. There are no steps of execution, which is weird then, because then how do we simulate a discrete event system simulation, which is all about state, using a framework where we don't have any state? And so that's what I've kind of asked you to do in the bonus, and what the book kind of gives an example of. And so if you go to this particular example, so imagine this is some spreadsheet that is capturing the essence of a discrete event system simulation. Now, remember our definition of a model, it represents it's an abstract representation of the system capturing formal relationships among system constituents. All we need to do now is, instead of thinking about the discrete event system simulation in terms of state, we have to think of it in terms of relationships, both within time and across time. What has to be true from time to time, and what has to be true within time. And if we can capture all of those relationships, then in an instant, our spreadsheet should be able to calculate the output of a discrete event system simulation. Now, what I mean by that is, let's start with something simple. I mentioned this before. If I know all of the inter-arrival times ahead of time, without running the sim, I can calculate all of the arrival times ahead of time, just by accumulating all of those inter-arrival times. So basically, this arrival time column here is just the previous arrival time plus the next inter-arrival, and that gives me my next arrival time. Question?
And you said that the in between time and arrival time, it's only for the spreadsheet situation, right?
What do you mean by the in-between time and the?
Like the thing that you just explained about how they'll need to track the system in between time and throughout time, and does that?
Oh, right. Well, I guess I'm saying that's how. Yeah, in a spreadsheet, that's how we're implementing it. If we were implementing it in MATLAB or in C, we might just be thinking about, okay, what's currently true at the current state. I set a bunch of state variables, and then I go to the next time. And once I'm done with the next time, I can forget about the previous time. And so we write programs differently in a MATLAB than we would in a spreadsheet. So what we just need to, rather than us thinking about what's true now and what will be true later, we need to think about what's true throughout space-time. Like in the 4D volume of space-time, what's got to be true both within time and across time.
Okay.
And that's how we come up with these formulas.
And then you said that mainly applies to the spreadsheet situation, right?
Right. I'm just saying that's how. It could apply to other things too. Maybe that helps you write things in MATLAB as well. But that's kind of the only way we can write it in a spreadsheet.
Oh, okay.
So that's how we can calculate arrival time. It's just the previous arrival time plus the thing next to it gives us the next. Fill that down, and we have all our arrival times. Well, that's easy. But how do we get to these more complicated things? Well, from there we can think about, well, how does the service beginning relate to everything else? Well, we can say for every customer, the time that their service begins is going to be one of two things. It's either going to be their arrival, in which case the system was idle when they arrived, or it's going to be when the last customer ended their time, when their service ended. So I just come up with a little max function here, where I say, what I know is true of every end time, every end service, or every begin service time, is that it is the maximum of the arrival time and the previous time service ends. So if the previous customer ended their service time way after this customer arrived, then I know that this customer's service is going to be delayed until this. But if it's the other way around, where the arrival time happened way after the previous customer's service ended, then I know that service can begin immediately. So it's a relationship that will be true for everything down here. And so that allows me to fill this down. Now the creepy thing about spreadsheets is that I haven't filled out time service ends. So I've, for the purpose of this lecture, I've filled these things in, but of course it's impossible to know these numbers without knowing these numbers. And so it's when you're writing this, say in your homework, if you fill this down, you're going to either get a bunch of zeros here or maybe a bunch of errors, depending on how things work. But you have to kind of have faith that once you fill in all of these things, then these numbers will end up shaking out and actually calculating correctly. But while we're writing it, these might not be correct. All right, so then the next step is that I have to figure out, well, how long are they waiting in the queue? This isn't necessarily something that I need for the calculations, but it's something that I might need for my performance later. And the idea here is if I know when they arrived and I know when their service began, I can calculate how long they've been in the queue just by subtracting their service begin minus their arrival time. So that's Q. That is going to be the case for every one of these cells. So I just go and implement that. Now the service ending time. I have to think what's true for the service ending time. Well, the service ending time is always going to be when the service began plus whatever the service time is. And so I can look to see when did this service time begin for this customer, when was my service time activity, which I knew beforehand, add those two together and I get that column. And now that I have this column, then magically this column should start working because this column depended upon this column. So then I'm almost done. How much time did they spend in the system? Well, that's just when their service ended minus their arrival time. And then that tells me how their response time, how much time they spent in the system. And that's another one of these. And then for the idle time of the server, we have another one of these max things here. It's either going to be idle for 0 time, or it's going to be idle for whenever the service began minus the previous time the service ended. So if this comes out negative, then this idle time is going to be 0. Otherwise, it'll be whatever positive number is here. And those relationships allow me to fill out this entire table, effectively allowing the math to do all of the hard work that your hand simulation had to do otherwise. And so we can now check our work. So here's the hand simulation that you did. Here's what Microsoft Excel or Google Sheets did for you. And so we notice that the spreadsheet time gets spread out across space. So whereas in our hand simulation, we had this time, this time, this time. We had time sort of separated out, but it was sort of, we kind of knew if we go down this here, we're going down in time. But in the spreadsheet, we've got 3 kind of columns that are times. So it's like we've spread out the interpretation across the spreadsheet. So it's a little harder to interpret, but all the info is there. So as an example, up here, you figured out that customer 3 departed at time 13. In order for me to figure that out, I go down here, customer 3, and then I go over, and her service ended at time 13. So it gets me the same answer. That looks good. All right, what's next? Here I see that customer 3, so I'm looking down here, like how long did they spend in the system? So customer 3 arrived at time 6. She departed at time 13. So I can say that, that this arrival time and this departure time, those are separated by 7. And if I look at these cumulative statistics, 16 minus 9, that also gives me the 7. So I'm seeing all 7s up here. If I look down here, customer 3, I have a column, spent 7 minutes in the system. So that also fits. And then, I might also want to see, all right, so let's see if I calculated this 16 correctly. So that's the total amount of time that all of the customers who've departed have spent in the system. And so if I think about, well, time customer spends in system, that's these. I've had 3 customers depart up until this time here, time 13. So I'm just going to add up these 3, 1 plus 8 plus 7, and I do get 16 out of that. So with whatever this was, a couple of formulas here, so 4 or 5 formulas and filling down, I now do all the work that you had done, by hand in this kind of tedious approach that could be very error prone. So if I haven't submitted your homework, and if you have, you can still resubmit. If you want to do the bonus, you can fill this out for your homework, and then you can then check to see if the numbers you get here, and you can just do a quick spot check. Did I get the departure times right? Well, that's easy to check. I can see when their service ended. And all these, 1, 12, 13, 18, should correspond. Departure 1, departure 12, customer 3 departs 13, and so on. So you can do a quick check to see if these numbers match those numbers. All right, any questions about this? About how to get your discrete event system for a single server, a single channel queue working in a spreadsheet? Okay, so the outputs here are highly variable, and that's because the inputs were variable. So our inter-arrival times kind of came from all over the place, so did our service times. Yeah, question?
Are you always going to utilize the same parameters? Like, for example, number queued and then number of people being served right now and all of that, like the 8 that was on the table?
Those are going to be for a single server queue or single channel queue. Those are typically the performance metrics that we're interested in. It isn't necessarily the case. So as we'll see, the reason why we don't use spreadsheets for everything is for more complicated models, it would be a real pain to try to figure out how to model it this way. And if somebody then comes in and says, well, what if we added another cashier? Well, then it becomes very difficult to figure out how to modify this thing to add another cashier and not screw something up. And so as you get into more complicated models, then we'll have more interesting performance metrics. But for kind of the toy example of a single channel queue with just arrivals and departures and a single server, there's not a whole lot that we can measure, but these are sort of the common things that we would measure. All right, so the outputs are variable because the inputs are variable. How do we make sense of the sort of simulation results with all this variability? Well, we are empiricists. This is an experiment. We've effectively ran an experiment and we got results out. If we ran this same experiment with a different set of arrival times and a different set of service times, we would get other results out. The same way, if we ran an experiment on a mouse, we would want to confirm that by running the same experiment on another mouse. The mouse, the particular mouse you're using, that is your input model. And so you need to run it on multiple mice because you need data from multiple mice in order to make an inference. You need to run a simulation on multiple inputs, which means you need to draw random numbers multiple times in order to get, and hopefully those random numbers have something in common. In this case, they're always a mouse. In this case, maybe they always arrive at 5 customers per minute or something like that. But there's a bunch of different ways customers can arrive 5 customers per minute. Some of them will be easier on your system and some of them will be harder on your system. There are a bunch of different ways you're going to have a mouse. Some mice are going to be healthier, some mice are going to be more compliant, some mice won't be. We need a variation in all of these mice the same way we need a variation in these inputs. And for each different input, for each different mouse, we'll get different outputs. And we pool all those outputs together in order to make an inference, and that's why we use statistics. And that's why we'll talk a lot more about statistical tests and trying to start with the tests that you learned in 380 and then grow them into a wider vocabulary of tests that can apply to a wider array of experimental designs. So, any questions about that before I'm going to move on to the lab? How many people know the whole relationship between Guinness Brewery and the t-test? People covered that before? Anybody heard that? None of you?
Yes.
All right, so there's one. All right. Just wasn't sure if this is a common example that they're telling staff. If it wasn't for Guinness, we wouldn't have the t-test. But we'll get to that later in a different lecture. All right, so yeah, so it's interesting. There's actually a really strong relationship between industrial statistics and biology, what biologists called biometry. And industrial engineers working at Guinness wanted to bring some of the data that they were using in biological experiments into industrial engineering. And that is part of, for purposes of improving the quality of beer and and reducing the cost of making it. And that's actually part of the way we got the t-test. But we'll get to that in a different lecture. All right, so a bunch of you have done Lab 2 right now, the hand simulation, and it's been submitted. I extended it so it was due last night. Muffins. And so I wanted to sort of, go over kind of the key things that I wanted you to take away from this lab, and kind of give some sort of answers to some of those questions, and just try to get you thinking more about our role as empiricists in doing this sort of simulation. So one part of it that was about modeling. And so far, when we've talked about entities in this class, we've sort of talked about effectively individual students, individual customers as entities. But in this lab, we kind of took a different approach where we said muffin batches were the entities. And that is sometimes an approach you can take. So if you model individuals, it's easy to handle, say, limited oven capacity because you don't have to worry about creating these partial batches. But it becomes difficult because suddenly you can have a lot of simultaneous arrival events. And so if you know that things arrive in groups of variable sizes, then sometimes it's better to model those groups as your entities. And so if you're trying to come up with entity types, sometimes batch of can be an entity type. So, and then there also can be lots of simultaneous departure events. So just group them all together. So that's what we do with batches. They give us single arrival and departure events. The only downside of that is sometimes the square peg of a batch doesn't fit into the circular hole of a resource. And you have to kind of shave the batch and create a partial batch in order for your simulation to move on. And that's what I hope you saw in the lab 2, is that there were cases where you had suddenly 35 muffins waiting to go in the oven, but only slots for 30 of them. So you had to split one of those batches up to create a partial batch of 5 so that you can put exactly 30 in the oven. And that's something that we kind of have to deal with here. In some of your sims later on, you'll actually see you use both. They might arrive as either a batch or individual, and then later on they get unbatched or batched throughout the system as is convenient, and then that might change as well. So you should keep in mind this idea of batching can be very useful in simulation. All right, so other sorts of systems where we kind of think about the number of being the random variable as opposed to the time between. And one of the ones I think a lot of people don't think about, although I've gotten questions about this, is in the past, which is why I bring this up, is actually the stock market. And so the same type of simulation you use to simulate muffin baking is actually also used to simulate the stock market. So think about it, every day you want to know how much does a price of a particular thing go up or down. And so you know that every day, that's when the time between samples is fixed. It's every day. But the amount that it goes up or down we don't know that. So that might change. It might go up a little bit one day and then down a whole lot the next day. And so these dynamic portfolio management models need these types of inputs in order for them to test different portfolio management strategies. In our muffin case, we needed to know how the muffins changed over time for us to test different ways in which we use the oven. We're managing the resource of the oven subject to arrivals that change the amount that they come in every day. And if you imagine if you were a quant working for Wall Street, you actually have the same problem to deal with. I have a certain portfolio that I need to manage. How many things do I put into this portfolio? And the value of those different things is going to change in steps every day. And so I need an input model that ends up generating, 5 muffins today, -5 muffins tomorrow in a realistic way. And so what they often use to figure out, like I just gave you how many muffins came in each day. I said there's 5 muffins in this minute, 2 muffins the next minute, and so on. But eventually you need to come up with that yourself. And they use what's called a martingale very often as a way to start. And a martingale is basically a stochastic process, and we'll talk about what a stochastic process is in a couple of lectures, but it's basically the idea that I'm going to put the constraint on my input model that the next tomorrow's number of muffins on average will equal today's number of muffins. So basically you can imagine that the next number of muffins is drawn from a distribution, and that distribution is centered around today's number of muffins. That would be one way you generate tomorrow's number of muffins. So I just gave you a string of numbers, but eventually I will give you a constraint like this one, and you'll just have to say, all right, so I need to draw the number of muffins from a normal distribution whose mean is the previous number of muffins. And then that would be you making the assumption that the number of muffins behaves like a so-called martingale process. And if you thought that actually, well, it's going to be above the average or below the average, there are these fancy terms called super martingales and sub martingales that actually depict these processes where you replace the equality here with a greater than or a less than. And so that's how you do input modeling in these types of systems. You often use models like these. This is a little advanced for this class. This is just a basic survey class. But if you start doing simulation models, especially for things like demand, or if you do go out and work at Wall Street, then you'll start seeing input models that will use these terms like martingale, and that's what it's all about, trying to figure out how tomorrow's number relates to today's number. So that was one of the things that I wanted you to see from this. Are there any questions on any of that so far? And we'll see in one of the next lectures, we'll talk about inventory management, and that will involve more of these types of models where we don't care about the time between arrivals, we care about how much arrives. All right, so these are sample data that each one of you individually should have gotten, something that looks like this. I forget what number, which page of the spreadsheet that I did this for, but there was at least one of those, the 0 through 9, where the average greedy was somewhere down here at whatever this is, about 3.9, and the average nearly full was up here around 4.15. From this single hand simulation, where we've done this greedy, and then with the same muffins, this nearly full, can we see here that it definitely looks like greedy ones spend less time in the system? Can we conclude that greedy is therefore better? Is this a meaningful difference? What do you guys think? Take 15 seconds and talk to your neighbor and come up with a good answer for me. Can we trust this? All right, let's bring it back in. So what do we think? Is this enough for us to go back to the muffin? We've been hired. We've been consulting. We've come in to consult this major baker, and they've asked us to evaluate whether to use greedy or nearly full. We've run this simulation, and we then conclude what? Can we conclude that greedy is better?
No.
Why not?
Multiple.
I hear multiple. What was that?
Multiple simulations.
Multiple simulations, multiple replications. It might just be that the particular muffin arrival schedule that went into both of these just happened to favor greedy. And it might be that if we stacked the deck a little bit differently, we could get another one that favored nearly full. And what we really need to know is, do we have a representative sample of all the different ways muffins could arrive? And if we have a bunch of those, we can evaluate this over a bunch of those different ones there. So we have sort of two questions here, statistical significance and practical significance. And and I'll get to practical here in a second, but what I'm claiming here is that by itself, this having a single sample here and a single sample here does not allow us to reach any statistical significance, because the muffin inputs coming in, we only have one sample, and we might have just gotten lucky that nearly full happened to be bad in this case, but in all other cases, greedy might have been better. Yeah, question?
So bottom line, it's that in order to like make conclusions, like accurate conclusions about each results that you get from your simulation, you need to run, have multiple runs of each.
Right. Yes, that's what I'm sort of saying. Bottom line is, to reach statistical significance, we need enough replications of these experiments in order for us to then see if we have generality. And so we can run multiple replications. That was part of the reason why I had you guys look at the last digit of your ASU ID and pick a muffin schedule based on that, is I was turning you into replication generators. Is that I was basically saying, imagine if you've got a different random string of muffins and you've got a different random string of muffins, and we grab 10 of you, then you all have different random strings of muffins. We can aggregate your results and maybe we'll get generality. So here's an example where I've taken all 10 of those and I put all the greedy ones here, and I put all the nearly full ones here. Now you can see that if I happen to have only run this schedule for greedy and this schedule for nearly full, if that's all that I ran, I might have made the opposite conclusion that I did in this previous case, and I would have said that, well, this nearly full is better than this greedy, so nearly full must be better. But now that I'm seeing them all together, then it looks like maybe I get a lot more evidence that greedy is statistically different than nearly full. But there's a problem with it. So in order for me to test for statistical significance, then I need to I can't just do this visually. I need to do some sort of statistical test that is objective, that has some sort of rigorous standard that people can get behind. So I have a bunch of data here, and I have a bunch of data over here, and I would like to make an inference about the mean. On average, is greedy better than nearly full? What is a good statistical test that you think I might be able to use? So we'll start with t-test. I've heard a couple people say t-test. So remember, a t-test is a test of means of a population, of two different populations, to see if these means are different. The problem with a standard so-called two-sample t-test, we have two samples here. We have a sample from the greedy population and a sample from the nearly full population. So a two-sample t-test allows us to analyze when you have two different samples. I've sampled from two different populations. The problem here is that a two-sample t-test requires that my samples from greedy were independent from my samples from nearly full. Were my samples from greedy independent from nearly full? The answer is no, but why?
The same numbers in the batch, but it's just a different policy.
Exactly, I used that. I heard several people say it. I use the same numbers going into both. I use the same muffins into here and the same muffins into here. Because I put the same ones into both, then these are not drawn independently. So they have to be paired. And so this method is actually one that we refer to as common random numbers. We'll talk about after the midterm. And it's a way in which we do what we call statistical blocking. And so the idea here, without getting into having you read all the details, is if I had two different types of shoe, I could put a population all in one shoe and a population all in the other shoe, and test to see if there's any difference between the populations. But I might have gotten lucky or unlucky and happened to choose a population of a bunch of people that maybe were all geriatric. They're all sort of old and at a very different use pattern than the athletes I picked over there. If I want to deal with that potential difference there, I could actually do something crazy. I could have every person in the whole group wear one shoe on one foot and the other shoe on the other foot. Two different types of shoes, all for one person. And then I would normalize for the differences, the natural differences between populations, so that I could actually compare. For this person, this shoe has a better wear pattern than this shoe. For another person, this shoe has another wear pattern than this one. So that's a reason why we actually want to pair things up, and why it's nice to pair our inputs up as well, because that way, if we just happen to pick an input that is, prefers greedy, by doing it on kind of both, then we can kind of see the relative for that particular input. So if this thing right here was one particular input model, I can say for this input going into both, then greedy was preferred for that one. But for some other input, I can kind of see, it kind of allows me to factor out the random differences that just come from the inputs. See a question here?
Yes, so in the previous example, the reason why you can do a paired t-test is because it's the same, like your samples are not independent, that's why.
That's right. The reason we can do a paired t-test is because these outputs are naturally paired together by their common input. And the reason we do that is it actually reduces variance so that we don't accidentally choose, like we could have just chose a bunch of random muffin orders for these and a bunch of other muffin orders for these, and we might have gotten similar results like this, but we might have gotten unlucky that the muffin group that we picked for these just naturally were an easier group to work through. Now that probably doesn't happen very often, that we would have gotten that unlucky, but especially for small numbers of muffin schedules, the chance of us accidentally choosing a group that has such a bias becomes larger. And so in order for us to deal with it, we just run one group into both and measure the difference on each one. And that's what these lines represent right here, is that a single pair of single muffin schedule went into both, and we measured the performance, and for that one single one, greedy was better. And if we look through all of this, since these are all paired together, there's some of these where there was almost no difference between, but they all kind of are tilting this way, which gives me even more confidence that the greedy schedule seems to be better. And so I can run, instead of plotting them like this, I can just subtract greedy minus nearly full and plot those numbers, and that's what I have here. And I can see greedy minus nearly full for all of the 10 different muffin schedules going in, I end up getting numbers that are all negative. So for the 10 different schedules, the performance measures for this all favor the greedy schedule. And what a paired difference t-test does is it just takes these differences and uses a one sample t-test against the hypothesis of 0. And it's clear here that if I ran a one sample t-test with these data against the hypothesis of 0, I would see there is a statistically significant difference. I can conclude that one population has a different mean than the other population. And so I've now shown statistical significance. One population is better than another. Are there questions about that? Yeah, in the back.
What if we did a single replicate which give us an obvious result, like there's a significant difference between the greedy and the default with a single replicate?
If you run a single replicate, kind of like where we started here, you could try to run a t-test on this, but what you find is that the p-value you get will be nowhere near the alpha of 0.05. So for a single replicate, your confidence intervals are going to be so large that it will be impossible to reject any sort of differences between these. It'll be impossible to reject that they're the same. So you basically don't get any info. That's why the reason we add data is we reduce confidence intervals, and that allows these p-values to settle down lower to a value that we can then apply some threshold. And I bring this up because my next sort of couple comments here are actually about the weakness of these approaches, is that the more data I add, the smaller differences I can detect, and the more likely that I will detect a difference. And so with one data point, there's almost no way that it's true that this one data point might be below 0, but if I actually ran the t-test, the p-value would be like 0.9 or something like that. It would not be below 0.05. But the more data I add, eventually this p-value, there's kind of an inverse relationship between data and p-values. If I went and ran 1 million simulations, even if these two schedules were almost not different at all, the p-value would probably end up dropping to below 0.05 because I've now increased the sensitivity of my experiment, but I've not necessarily detected a meaningful difference. So that's the difference between statistical significance and practical significance, is that I can always drive p-values down below 0.05 by taking more data. Because there's going to be a difference. You could say, I'm going to test the hypothesis that Professor Pavlic's mood is being influenced by Pluto. You know, Pluto is, I guarantee you, having some effect on my mood right now, regardless of whether it's a planet or not. But whether a hypothesis with or without that, like if you built a model of my mood that included Pluto and a model of my mood that didn't, the one that included Pluto would most definitely sort of better approximate what's going on. But the difference between those two models would be almost nothing. So if you took enough data, you could detect the effect of Pluto on my neurochemistry. But why would it matter? Because in the end, for all practical purposes, you don't ever need Pluto to sort of gauge, whether I'm upset or not. So this is a major problem about practical difference versus statistical significance, and we'll talk about that here. The other major problem here is that in your simulations, we measured 3 outputs. You measured the total time, the average time in system per muffin, you averaged the average oven utilization, and you averaged the maximum queue length. Now, it might have been up here, my paired t-test showed me statistical significance, but down here, it doesn't show me statistical significance. So for these things here, so the question is, which output do I use? If I would have arbitrarily chosen oven utilization, I would have gone back to my stakeholders and said, look, there's no difference between greedy and nearly full. So why did I choose average time in system and found this difference? You could say, well, what if I come up with a bunch of different things I could show them, and I'll run a t-test on every one, and maybe one of them will end up showing a difference. Well, then you end up fishing. Remember, t-tests are wrong 5% of the time. So if I do 1 million t-tests, there's a high likelihood, a high chance that I'm going to end up finding a difference that isn't actually there. So this is the so-called fishing problem, or the multiple comparisons problem. And so that's another thing we have to deal with when we talk about statistical significance, is how to deal with that. And we'll talk about that later in the class, but basically it has to do with, as you add more outputs you're looking at, the alpha that you use for each test has to be adjusted to deal with the fact that you're now fishing. 2 questions. I got the one first. See the poster?
Yeah, so literally practical significance is just like doing what makes sense, like pretty much.
Well, I'll get to that, but practical significance has to do with, as engineers, I've designed this particular device to withstand differences in, I always do like a plus minus, like I've got some safety factor. Basically what we'd say is the detected difference within my safety factor? If it is, then I don't really care. So why gather more data if the difference, like I could say I didn't detect a difference, but if I took more data, I could detect a difference, but if I detected it, it would be well below my safety factor. In that case, it's not worth the effort of taking more data.
So it's basically kind of like once you reach like an optimal level, you don't need to continue collecting like a ton of data to statistically prove it.
That's right, because the more data you collect, the more sensitive you make your tests, but that sensitivity might not be worth the cost. There's another question? Okay. All right, so this is my sort of statement here. Even if we do deal with this multiple comparisons problem, again, how do we deal with this practical significance? And that's the reason why unfortunately, the way we normally structure statistics, at least in the engineering and in a lot of other disciplines, it's changing now in business, it's a little bit changing in biology, but we put linear models at the end of your stats courses rather than up front. Ideally, we should teach you 14 weeks of linear models and a week of hypothesis testing. And that's kind of the modern way of thinking. But the traditional way of educating is 14 weeks of hypothesis testing and 1 week of linear modeling. The linear models allow us to do other very interesting things. So for one, they allow me to more simply, and I can do this with hypothesis testing too, but it's simpler in linear models, test a wide range of treatment levels. And I tested greedy, so this on the x-axis here is an oven threshold. It's a threshold of how many muffins are in the queue before I open the oven up. And greedy would be 1, and nearly full would be 20. But why 1 and 20? I could have also tested 5, 10, 15, 30. And so I can rerun my simulations for all of these different simulations, all these different thresholds, and take my different outputs, and I now get these complicated patterns across here that I can then fit with linear models, and I can start asking what's the strength of these particular treatments on these particular outputs. And this allows me to say that, as I increase my oven threshold, I get a small increase in the time and system, and I can quantify to my stakeholders roughly, what this is. So for every 5 that I add, I get roughly this amount of difference here. So now you could say the hypothesis testing perspective would be, is this slope different than a 0 slope? And that's fine. But a better way to do it is to say, let's find the very, very best model I could find. And once I find that very, very best model, with or without Pluto, whatever it is, I can then come back to the stakeholders and say, the effect of Pluto is really tiny. In a world with Pluto to without Pluto, the slope of that line is really small. If you care about that tininess, then fine, go ahead and use it. But if not, then don't worry about it. But here I've quantified the effect size. And that is going to be much, much more useful in an engineering context. And so that's one thing that linear models allow us to do. The other things they kind of allow us to do is, so this was at the service time of 7. It turns out there is an interaction between oven threshold and service time. So this was the service time of 3, that's what you guys simulated in lab. If I increase my service time to 7, it flips the relationship. So now, whereas here, this is saying if you can get muffins in and out of the oven quickly, then it's best for you to basically, tilt towards a greedy policy if you care about getting as many muffins out as fast as possible. But once your muffin oven goes to taking 7 minutes, then now I get a flipped relationship where now I actually wait for as many muffins as possible before I put them in the oven. And if I go even further to like 14 minutes, I get these interesting structures. It's almost these transition regions here, where not only is it sort of gets reduced here, but there's in the nearly full policy, there's kind of these 2 regimes where if I'm lucky, I'm down here, but in many cases I'll be unlucky and up here. And so that is even more of a reason to not just go nearly full, but to go all the way to 30 so you're guaranteed so that all of your schedules will be here in the low times, as opposed to here where you're kind of flipping a coin, not knowing if your schedule is in this group or in this group. Question? Yeah?
What tools do you use to make this?
This I actually just plotted in MATLAB, and I use a generalized linear mixed effects model to generate this line here. So, which again, this is a more advanced statistical tool that will flirt with these ideas. But if you're interested in these things, let's say a more modern way to do your stats are these linear models. And then, so you say, well, what if I don't have something that fits the assumptions of a linear model? Well, there are these things called generalized linear models, which is a way to pre-process your data so it does meet the examples of the models. And then if you want to deal with these blocking effects, well then I create what's called a random effect inside my linear model, which basically my different muffin schedules are a different random effect. And so all of this stuff can be added into these linear models, giving us a whole lot of power in the analysis that we don't get with a simple t-test. Yeah?
A couple of questions. What policy did you use to plot these diagrams? I mean, is it both policy at the same time? I mean, you...
Well, no, so the greedy policy is threshold 1, the nearly full is threshold 20, and all these are policies we didn't even try in lab. So policy that's greedy, and that's nearly full. And these are other policies that I tried on my own.
Isn't it the capacity of the oven? I mean, is it the our policy? I mean, threshold refers to our policy to...
Sure. So yeah, I guess what I'm saying is that the treatment here, or the thing that I care about, are just different factor levels. And so I'm saying, how much does threshold matter? Okay. And I'm saying that, well, before I just asked threshold 1 versus threshold 20, but now I'm seeing that, well, it turns out that it's not just an on-off effect. There's this smooth effect that threshold was having. And so even back here, I thought that here it almost looks like threshold has no effect on oven utilization. Turns out that was because I was at service time of 3. Once I go to a service time of 7 or 14, then threshold has a huge effect on oven utilization. So, yeah.
So here, the capacity of oven is constant, basically.
The capacity is constant. It's always 30.
Another question, in t-test, we had in the denominator, we had a square root of n, and that square root of n comes to denominator. I'm talking about...
And I'll get into that in
yes.
future lectures. We'll talk about the t-test in detail.
Oh, okay.
So let's take that offline.
Okay.
All right, so that's my pitch, is to sort of say what I want you to take from lab 2. Variation matters. Simulation is really hard by hand, but it is super easy by computer. So you can test all these what-if scenarios and get a lot of really rich dynamics out. And if you have the right statistical tools, you can summarize these in a way that'll be really attractive for your stakeholders. All right, so if any other questions, feel free to come up to us after class. Here's your attendance question for today. And I guess what I'll ask is for I said that delays in a simulation are the effect of misalignment of what? So there's certain things that went into the simulation, and if they're misaligned, they generate delays, and that's interesting to us. What were those things that get misaligned? And then that's all I've got for you today.